it, and we have known what dimension of the physical quantities are, and how we write them and how we present them. That's what we were looking at the other time. Nalubega. Mary? Yes, Mary?
Teacher. Yes, teacher.
Yes, I'm sorry we started late.
Yes, teacher.
We started a little bit late because there was another teacher having a lesson, so I could not again come in, okay? I had to wait for him to finish. Okay? Yes. But nevertheless,
Okay.
let's continue. I'm seeing Sandra is getting challenge of connecting our microphone. Yes. So without wasting time, because I've already, those who were there at that time, I've already given the preamble. I've discussed at length what I expect from you in this paper and what we expect from you in physics generally. Okay? And when I talk like this, I'm looking at the background because today A-level result is out. Because when you look at those people have done, they were not paying attention to whatever we were telling them. That's why they were challenged. They didn't perform to our expectations. But now your group, we need to be steadfast so that we perform to our expectations. Are you together? Yes. So without wasting time, let me share my screen. Are you able to see my notes and the space? The space?
Yes.
All right. All right. Good. So we were looking at dimension. We said dimension refers to power to which the fundamental quantities are raised. The power to which the fundamental quantities are raised. And we use powers to which the fundamental quantity is raised. That's what we call dimension of a quantity. Dimension of a physical quantity. And we said it's not only one, or we can say refers to the way a derived quantity is related to the three fundamental quantities of. So when we talk of this, we are basically referring to sorry? We are basically referring to the fundamental quantities. So we want to see how the three in mechanics. I said we have more in physics. We have more than three basic quantities. But when we come to mechanics, we look at what we call fundamental quantities. This is length, and when we are talking in dimension, we present length with capital L. Then we have time, which we present with capital letter T. Then we have mass, which we present with capital letter M. Then when we come the way with presentation, I'm just giving a quick recap of what we look at that time. Presentation, we said when you're presenting a dimension is presented or symbolized by a closed bracket. This is what we call a closed bracket. Okay? So we gave a case example, like when you look at the derived quantities, we have given very many, and we have seen how we derive them. We gave a case example of area. When you look at the dimension of area, we know that area is equals to length times width. Length times width. So when you are presenting, you present the dimension of each. So dimension of length times the dimension of width. And we discover that length, we use letter, so it becomes L, time. Width is also length, because we still measure distance, so we still also present it as L. So we find that dimension of area will be equals to L squared. We can look at volume, we can look at pressure, any derived quantity that you know. You can talk of density, you can also look at density. We know density is the mass per unit volume of a substance, so dimension of density will be mass You get the dimension of mass, then you also get the dimension of volume. Okay? So for mass, mass is a fundamental quantity which is presented by m divided by volume. Volume we said is a base area times height, which will give us L what? L cube. But we don't leave it like this. We put them in indices form, in power form. We put them in power form. So this one will give us density. Density will be m L per. So now that's why now this one. Now this is the power for L is -3, then power for m is 1. But we can't write there 1. So that's what basically we look at the other thing. And also we proceeded. We look at the uses. Why is that? It's very important to study dimension. Dimension is very important because it helps us. It helps us. All the equation you use in either in mathematics or in physics, all are derived because of the concept of dimension. Uses of dimension.
Excuse me, teacher.
Yes?
Yeah, teacher, question.
Yes, please.
Yeah, like the you're writing those dimensions. Should you put the bracket on the dimension or on the word? Those brackets.
You put it on the word, okay? Because you are defining a quantity. That is, we are getting dimension of that particular quantity. Okay?
Okay.
Yes.
Okay.
Like for the case of length, we use letter. Now when you're after writing the dimension, now you present the symbol. Now you come to the presentation, the symbol. So for length is L. Now when you come to width is also distance, which is still length, right? So that's why now you present, here we are presenting the symbol. We are presenting the symbol. So the dimension of length is L, then the dimension of width is also L. So that when you get, these are the same quantities, so you multiply them. Are you together?
Yes, teacher.
Yes. We can look at maybe if you also we can, let me give an example. We can look for maybe pressure. Let's look for pressure. If you're getting dimension of the pressure, the quantity we have in pressure is force over area. So you get the dimension of force. I see that. Dimension of force divided by dimension of what? Area. So after this, now this we have derived for force. Remember we said force is equals to ma. You get that? So from here you can get for force.
Yes.
You can get you can derive the dimension for force. Then you come and put for the area, which we have already got. So you present it with the quantity. Then after putting the dimension of that quantity, now you use the symbols. The symbol is either in term of either length, time, or mass. Right together. So in any dimension we are going to be dealing with, dimension of any physical quantity, it must either have L, T, or M. Anything outside this, then is not a dimension of any quantity. Right together.
Yes.
Yes. So you must find way of deriving the dimension of that quantity to contain L, T, and M. Otherwise, it will not be dimension. So we discussed all those things the other time. Now we are looking, now we also went ahead and look at the uses of dimension, and there are only two. There are only two. The first one, we use it to check. Use to check how valid or the validity of a given equation, the validity of an equation, or to check whether the equation is dimensionally consistent. Dimensionally consistent. And this is very important. Very important. Then the second one, we use it to derive equations. We use it to derive equations. We use it to derive equations. There are very many formulas that we use always in physics. Like when you go to paper 2, there are very many formulas that we use there. You come to paper 1 physics, there are very many formulas that we use. All those formulas you see, before they were brought out, they were verified using dimensions. Because any equation which is not dimensionally consistent, then that equation is not correct. Are you together? Are you together, members?
Yes.
Yes. Let me hope you are following me very well. If there's any question, please raise it. Are we still together?
Yes.
Okay. So we use dimension to check how valid a given equation is, and that one we call it, that equation must be dimensionally consistent, which means if we talk of an equation being dimensionally consistent, we mean the dimension of that function in the left must be equal to the dimension of that function in the right. Once they are equal, then we say that equation is dimensionally consistent. Then apart from using it to check the consistency of a given equation, we can also use it to derive an equation. We can use it to derive an equation. Are you together?
Yes.
Yes. So now let's look at them one by one. The two, let's start with checking the validity of an equation. How do we check the validity of an equation? Checking the validity of an equation, or dimensionally, what we call dimensional homogeneity. When we say some equation is dimensionally homogeneous, so that equation must be dimensionally consistent. Are you together?
Yes.
So we say when the dimension on the left hand side of the equation are equal to the dimensions on the right hand side, then the equation is said to be dimensionally consistent. And one is dimensionally consistent, then it is a valid equation or is a correct equation. So for dimensionally consistent, dimension homogeneity. So the dimension of a fixed quantity, the dimension on the left hand side must be equal to the dimension in the right hand side. Dimension in the left hand side must be equal to dimension in the right hand side. Then we shall say that equation is dimensionally consistent. Are you together?
Yes.
Yes. If that is true, now let's give an equation that we know in physics. Like the first one I've given you there, let's look at that one we have there. The equation is the velocity of a wave along a flat string is given by, so the equation they've given us equation. We want to prove whether this equation is valid or is dimensionally consistent. We have V equals to the square root of TL over M. So from the equation they've given you, T is not time. Don't take it as time. They will define for you, like in the equation they've defined, they have said T is the tensional force. So T is the tensional force or just tension in the string. We know the factors that affect the velocity of a wave in the string and a resonance. Do you remember that? I believe you have looked at that one in paper 2. Not so?
Yes.
Yes. So we have the tensional force. Then L is the length of the string. We know how the length. Here we are not interested in expansion, only that we want to prove the equation that we have been using. Whether the equation the teacher gave you, whether it's correct or not. Okay? We want to prove. Then M is the mass of the string, which from the notes, when we look at the details in paper 2, we said is the mass per unit length, or the thickness, or how thin a given string is. And the thinner the string, the louder, the higher the frequency. You remember that? And the shorter the length of the string, the higher the frequency. Not so?
Yes.
Yes. So that's why you see that in a guitar we have to tighten it. Why do you tighten it? So that it increases the tensional force, so that it produces a good sound. And because frequency, remember frequency is directly proportional to the frequency, to the velocity. You remember that? Velocity is directly proportional to frequency. The higher the frequency, the higher the velocity. That's why we get this equation now. V is directly proportional to F. That's why we have this equation. V is equals to F lambda. I think that.
Yes.
Where lambda is the wavelength. Is the wavelength. So we are not interested in looking at that, but our interest in this case is just to prove whether this equation is dimensionally consistent or is equation is it correct. Are you together?
Yes.
Yes. Now let's prove that. Now the question is saying that show that the formula is dimensionally correct or dimensionally consistent. So let's work on it. So we shall take side by side. You don't take all of them at once. But before we start looking at it, let's recall from our indices. Our indices. We said a square root is the same as a square root is the same as
Half.
a half. Then the cube root is the same as a third. Okay? Then 1 out of a is the same as 1 to the power negative 1. That is indices. I'm just trying to, because it's going to help us in understanding this one further. Okay? Yes. Then we also have to remember, if I have a to the power m times a to the power n, the law said we said n plus what? We add the what? The power. Then the second one, if I have this, divide by that. What do we do to the powers? We subtract the powers. Not so? Yes, these are the concepts that is going to help us to get the correct answers. So after making that flashback, then we can now go and look at the question side by side. We check the left hand side. After checking the left hand side, we also go and prove the left hand side. And once the left hand side is equal to the right hand side, then that equation is it correct or is dimensionally consistent. Right together? Now let's look at, so our equation is V is equals to the square root of TL over M. So considering, let's start considering sides. Considering the left hand, considering the left hand, considering the left hand side, consider the left hand side, and in our left hand side we have velocity. So we have to get the dimension of velocity. Dimension of velocity. And remember we said velocity is the rate of change of displacement. By definition. So you must also know definition of this. By definition, velocity is the rate of change of displacement. Is the rate of change of displacement. So which means we can say speed is equals to distance or displacement or distance divided by time taken. So if that is true, so we know that, so now the dimension of velocity is equals to, now we are going to get the dimension of displacement divided by dimension of what? Time. So it implies now the dimension of velocity is going to be equal to, displacement is a distance moved in a specified direction, and distance is measured in terms of length. So which means this one is our L, divided by time is a fundamental quantity which we use, capital letter T. So therefore, the dimension of velocity will be equals to L T to the power negative 1. That is, this is our left hand side. So the left hand side is equals to T, LT to the power negative 1. We leave it like that. We leave that one. Then we go to the right hand side. We go to the also considering the right hand side. We have to go and consider the right hand side. When we come to the right hand side, we have the square root of T L over M. We have the square root of T, where we have This, we have tension, we have length, then we have mass. So, but now this one, you are going to write it like this. So this one will be T L over M to the power a half, because the square root is the same as a half. So in this case now, to get the dimension of this, we are going to get dimension of tension, dimension of tension, dimension of tension, time the dimension of length, time the dimension of length, divide by dimension of mass. But remember, everything is under a square root, which is to the power half. Okay? Are you together, members? Are you together?
Yes.
All right. All right. Nalobeg, are we together? Mary, are we together?
Yes, teacher.
What about Sandra? Sandra, are you together? Or team, are we together? Yes? Are we together?
Yes, we are together.
We can proceed, eh?
Yes.
All right. All right. So after that, we know that we have now dimension of tension. We have dimension of tension, time, dimension of length. I'm just repeating what we have already written down. Divide by the dimension of mass. Everything is under to the power a half. And remember from our law of indices, when a number is raised to another power, we multiply the powers and we distribute the distribution of powers. The distributive law, you must also remember that. So now after that, come and look at, remember tension is a force. So what's the dimension of force? So tension, what's the dimension of force, sorry? What did we get the other time when we are doing it? We said dimension of the force is given by dimension of, because using F equals to M what? MA. We said is mass time acceleration, mass time acceleration, mass time acceleration, because it's a force. Okay. So we shall have mass, which is M, time for acceleration. We remember that that time acceleration is L t to the power negative what? 2. That's what we got at that time. Okay? So it means now tension, the dimension of tension will be equals to M L t to the power negative 2. That's the dimension of tension. Mass and length, all those are physical, those are fundamental quantities, which we just use single letters to present them. So now it implies now we shall have dimension of tension, which we have got is M L t to the power negative 2 time length times length, which is L, divided by dimension of mass, which is M, but to the power a half. So, but before we open this, before we distribute the powers, let's first simplify this. So it means now we shall have law of indices. I've just given you law of indices. You multiply the one with the same base. So M is alone, but L you have L times L will give us L squared. Then T is alone, so it will give us T to the power negative 2 out of M, but still to the power a half. But even before distributing this power, you can see that this M is here will cancel with that M. So which will give us, now we shall remain with only L squared T to the power negative 2 divided by, now is 1 only, but still to the power a half. This one will not change anything. It's a constant. We said the dimension of a constant is 1. So dimension of a constant is 1. So which means we shall have now L squared T to the power negative 2, but to the power half, So if you recall from our indices, I said if I have AB to the power n, this power is going to be distributed for all of them. So we shall have a to the power n, also b to the power n. So for that case, so it implies that L squared t to the power negative 2 to the power half. So when I take the power inside, so I will have L squared times a half times t to the power negative 2 times a half. So this one will go with that, this 2 will go with that. So you find that we shall remain with L to the power 1, then t to the power negative 1, which is equals to L t to the power negative 1. Have you seen that? Have you seen that?
Yes, teacher.
This is it. This was our right hand what? Side. So now when you see, you ask yourself now, you ask yourself, is the left hand side equals to the right hand side? Is it true?
Yes.
Because the dimension, the left hand side we also got L
Yes,
is the same, right? So now we are going to say it implies now the left hand side is equals to the right hand what? Side. If they are equal, then you conclude hence the equation is dimensionally correct. The equation is dimensionally correct. Are you together?
Yes.
Are you together?
Yes, teacher.
Have you got that one?
Yes, teacher.
So let's see. Have you seen what they have got here? In the worksheet here, have you seen?
Yes.
So the left hand side is equal to the right hand side. Since they are equal, since the dimension they are equal on both sides, then the equation is dimensionally correct. As simple as that. So let's go to number 2. That question 2 you are seeing there. Let's go to question number 2. Question number 2. In number 2, please can you mute your microphone? Please, can you mute? You unmute only and only if you want to talk. For now, let's first unmute. Let's mute our microphone, please. Stephen, can you unmute? Can you mute, You mute. Or minimize the noise in the background. So in number 2, they are saying that the period T, we know period is time of a simple pendulum is given by, so T is equals to 2 pi the square root of L over D, where L 2 pi is the dimensionless constant, D is acceleration due to gravity, then L is the length of the pendulum. So let's try to hurry up. Only 10 minutes remaining so that we go for the break. So they want us to show that this equation is show that the equation is dimensionally consistent or correct. So we just take sides. We say consider the left hand side. They have said T is the period. Period is time. I'm just giving this one, but in exam you don't need to write for me this, please. Period is the time taken. Time is the time taken for one. Complete oscillation. Or cycle. So the fact remains that period is time, and time is a fundamental quantity. So which means the dimension of period will still be equals to time. Right together, the dimension of period will still be equals to what? Time, because period is time. That's our left hand side. So is there any other quantity in the left hand side? No. We go to the right hand side now. So also considering the right hand side. In the right hand side, we have 2 pi, the square root of L over G. L over G. Now you have to remember, we said there are certain quantities which are dimensionally, which are dimensionless. We gave a case example of a pi, any number, 1, 2, those are dimensionless constants. And if we have dimensionless constants, there are dimensions. So we say recall, dimension of a constant, dimension of constants is 1. No matter what, pi, what is 1. Any number and a constant like pi, their dimension is 1. So now which means we shall remain with, so we shall have 2 pi, the square root of L over G. So for the matter of consistency, we are going to say dimension of 2 pi. I think that dimension of 2 pi, the square root of, so we get the dimension of length, just to be smart and organized, dimension of length, divided by d, which is acceleration. D, acceleration due to gravity. The fact still remain is acceleration due to gravity. Okay? So, but what is the dimension of acceleration? Let's go back. Acceleration. Dimension of acceleration. For the interest of time, let's just go and check from here. I remember we derived it at that time. Acceleration is a change in velocity, which we got. Acceleration is L t to the power -2. That is the dimension of acceleration. Then dimension of length is equals to L. Then the dimension of 2 pi is equals to 1. Dimension of 2 pi is what? 1, because it's a constant. So now when you put it back, so we shall have, now this is 1, the dimension of that is 1. Now instead of writing the square root, I'm going to replace it now with a half. So I'm going to say, I open this open bracket. So I put the dimension of L, we said is of length is L, divided by acceleration, which we have said is L t to the power -2, but to the power a half, to the power a half. So now when you look at that, so which means we shall have this one will have no effect. This L will cancel with that L, right? This L will go away with this L. Then we remain with 1 out of t to the power -2. Take away that, but still to the power a half. Now, when you recall our indices very well, I said if I have 1 out of A is the same as A to the power -1, and the reverse is true. Now, this time the power is negative. So when I want to remove this negative, I just get the reciprocal of this. So when you get the reciprocal of this, you get t squared. You just get t squared equals to that. So when you take the power inside, when you distribute the power, you'll have t squared times a half. T squared, you find that this and this will cancel with that. So you find that we remain with the t. So in the left hand side, so the dimension in the right hand side is equals to t. Dimension in the right hand side is t. What did we get in the right hand side? In the left. In the left is what? Was what? Was the t. Then in the right also we also have t. So what is the equation? What is that equation? So you come and say since the left hand side is equals to the right hand side, therefore you conclude like that. Therefore, the equation is dimensionally. The equation is dimensionally correct. Dimensionally correct or consistent. Dimensionally correct or consistent. Have you seen that? Members, are we together on that? You can see what they have there. So dimension of length, dimension of what, we get that equals to that. Since the left hand side is equal to that, then the equation is dimensionally consistent. Are you together now? Hmm? Please be
Yes,
audible enough.
teacher.
Be audible enough, please. I want to get you. Are we together?
Yes, teacher.
So we know how to prove when they say that show that a given equation is dimensionally consistent, you know how to prove it. So you take the dimension on the left and you take the dimension on the right. If they are equal, then we say they are dimensionally consistent or dimensionally correct. But if they are not correct, there are times they give you when they are not correct just to find out.
Yes,
So
teacher.
if the dimension on the left hand side is not equal to the dimension on the right hand side, then that equation we said is dimensionally inconsistent. Is dimensionally inconsistent or incorrect. Is dimensionally inconsistent or incorrect. That is, if you find that the dimension on the left is not equal to the dimension on the right. Be very careful with that. Don't just assume that they must always be equal. There are times when they are not equal. They just give you to confuse you. Okay? Then also there's another fact that we need to know. Check this NB is here in the NB. Dimension can be added or subtracted. Dimension can be added or subtracted. Dimension cannot be added or subtracted, but for any equation to be added or subtracted, they must be of the same dimension. They must be of the same dimension. They must be of the same dimension. So after the break, we shall come and look at that. But let's first digest this. How we prove that a given equation is dimensionally consistent. Is there any question on that? Is there any question on that? Members, is there any question on that? How we prove? Yes, Otim. 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 Yes, Otim.
When you're presenting,
I think you have problem with your microphone, please. You unmute. You unmute. I mean, you mute. You mute your microphone, please. You mute. Yes, Sandra? You only unmute if you want to say something. Yes, Mary? Mary, can you unmute? Mary, can you unmute and say something?
I have no question.
Everything is clear, right?
Yes.
Okay, what about Stephen? Stephen, can you unmute and talk? Unmute your microphone and talk. What about Sandra?